time to move on to a little bit of other news about the pathway to discovery in astronomy and astrophysics for the 2020s. What the heck does all that mean? So what I'm talking about here is the Decadal Survey. It's a every 10 years, astronomers get together. A panel is picked essentially of people that are very active in research, and some of the best astronomers in the field decide what is the most important direction for astrophysics and astronomy to go. What mission should be launched, what gaps need to be filled, what do we need to be doing to engage with the public and also to engage with the science. And this was recently published, and we're going to go through all of these, not in detail at all, but you can see the sorts of things that the teams worry about. And the very, very top, let's break it down into what's going on here. Up top, we have the big goals. So that's what's important. What are we trying to do? We want to go find habitable worlds, other Earth-like planets out there. We want to take a look at worlds and suns in context, because planets don't just hang out on their own. They're around a star. And if that star, say, has too much X-ray flares coming off of it, it'll fry all the life. So we need to understand how the two evolve and work together. Also, it's important for Earth. Our own Earth is around our own sun. We need to understand how the sun works. We measure it every day, but a deep understanding of these environments is needed. Also, new messages and new physics. What are we talking about? Well, things like gravitational waves. How do we leverage those together with other thoughts at other observatories? So this is the stuff we're talking about. Deep thoughts of coordinating observations to get us the best new view of the cosmos. Now, in order to do it, you need to have some space-based tools and ground-based tools. You need to have the vision of the future to be planning things that are decades off. Again, the Webb was in the planning in the early 90s, and we're hoping to launch later this month finally. So, you know, these things literally do take multiple decades to pull off. Now, some of the science that's going to get done, again, the environment around stars. When you have stars just being formed, planets get formed then too. What are those environments like? What do the planets go through as this happens? Is there a reason why in our solar system we have an Earth-like planet where we do, but in other ones we have the gas giants closer? Was it due to something in the environment while Earth was being formed and the sun was formed, or did something else happen? We don't have a companion star as far as we know, but understanding how binary solar systems and how that affects the planets is very important as well. Sometimes the binary stars are very faint. Little brown dwarfs can swing in every once in a while and wreak a lot of havoc. We also need to understand how stars and galaxies and the gas within them interact. When stars evolve from molecular clouds, these are things, again, the Webb is going to study. We're going to learn more about it, but we need to have the plan for when we learn what Webb's going to tell us, what's next. How do we take that information and leverage it further? So we're going to say these stars formed, supernovae are going to go after that, sends jets and winds more material back out into space. It cools and gets recycled sometimes. We see evidence for flows, inflow in galaxies. But what does that really mean for the evolution of galaxies? We need to study galaxies throughout all of time to really be able to make these decisions and understand these processes. Like I was saying, also the multi-messenger part of it, where we take gravitational wave information, black holes that are colliding. Once we start to get a real family of black holes, and we know what rates different masses are accreting together and forming together, we'll have to figure out, well, how did they get that way? Was it pairs of stars? We're going to start to see galactic size black holes merging, or it'll be from dwarf galaxies that merge together and coming in together. In fact, there was a story I saw today about, I think it was Draco has a nearly 4 million solar mass black hole in it, a dwarf galaxy around our own. So what is that doing there? And what does that mean elsewhere? Well, our gravitational wave astronomy can tell us about that. But there's also neutrinos. We have neutrino observatories that work now, but they don't give us a great picture of what's happening. We tend to say we got a bunch of neutrinos from that direction. That's about the best we can do. And the direction isn't very precise. We need more precision, because when stars explode, they give off neutrinos. When black holes merge, probably not, but a black hole and a neutron star merging might give off neutrinos, and certainly two neutron stars merging creates all sorts of bling. We've talked about that one before, and also makes gravitational waves and neutrinos. So we can see all of this happening together. And then, of course, we have photons, good old light, good old-fashioned light in the infrared, in the UV. We need bigger telescopes to provide us even more details for that. And this is what the Decadal Survey came forward with. And they told us that those are the important science topics, but we need to have great observatories in order to do great science. In the past, these are the observatories we had. We had Hubble, Certif, which became Spitzer, Chandra, and CRGO, that's the Gamma Ray Observatory.
Compton Gamma Ray Observatory.
Gamma Ray Observatory. So these were the 4 great observatories we had. And now we do have Webb coming, but it's not truly a Hubble successor. It works in a different wavelength range. It is designed to do a certain kind of work. It's not, it'll fill in certainly, and it'll expand our capabilities where we need them when we did, but we need these telescopes. These are the next ones we need. The exact design will change, I'm sure. These are concepts of how they will work, but Origins is going to be a far infrared telescope that's going to be able to look at literally the origins of stars and the origins of these things, and look, find things in the far infrared in some of the coldest environments where the action is happening. HabEx is going to look at habitable planets, actually go and resolve them and say, we're going to see these planets, and that means you can do spectroscopy on them if you've resolved the planet. It might not be more than a few pixels, but if you have it separate from the star, you can start to analyze those planets, and it'll do it much, much further away. By the way, Origins is supposed to be something like maybe a 10 to 15 meter telescope across. So that's not small. These things are small. Louvre,
Tiny little thing.
Good. Louvre also is another one, looks very similar to the Webb design, but it will work in the ultraviolet, it'll work in the optical, and also in the near infrared, but we'll have a big shield like that to keep it cold and to protect it from stray radiation. And then lastly, Lynx, a brand new X-ray telescope to increase our sensitivity and the resolution. We need to get down in those AGN, active galactic nuclei, where the black holes are accreting material, and see where those X-rays are coming from. By combining all of these sorts of new great observatories, we can push the frontiers of science and astronomy into these sorts of territories. So we're talking about really moving things back towards the age of the universe, back towards the CMB polarization ideas. You do that with gravitational waves. You can't see past, the cosmic microwave background, but with gravitational waves, we might be able to get more information about what's going on inside of there. So these are the exciting frontiers they're talking about. They say, let's plan them now. Let's think about a giant array, a new array to be, bigger and better, maybe put it on the moon. This is certainly a very fanciful diagram here, but new arrays to replace the aging radio arrays that we have now, ones with increased capabilities. We need new telescopes for a new ice cube telescope. That's the one that does neutrinos. So all of these working together will certainly expand our capabilities and certainly push things forward. Certif is already X'd out on this one because we no longer have Spitzer. Anyway, Webb is coming. It costs billions, and then we have all these low-cost missions that only cost millions, 300 million, cheap, just like that, to send these ones. They also mentioned, this Decadal Survey, that we should have medium-priced missions, ones that fill in that gap. It's nice to have a $300 million mission, but you have to lose capabilities to keep it that cheap. And it's great to have a $5–10 billion mission, but those you can't afford to do very many. So they suggested that they should fill in between these with handfuls of missions that maybe cost, $1 billion or $2 billion instead of tens of billions. So invest a little more, get more capability, but don't put all your risk into it either. So not all of it was about technology. Some of it was about the culture and the people that are doing the astronomy and doing the science. And it turns out if students start wanting to do physics and space, they usually don't end up doing math and physical science. They leave. They go into the social sciences. They go into biology. They go into humanities and other things. And the question was why? We're losing diversity. We're losing people that have an interest. And they felt that astronomers and physicists, we need to put an effort into understanding why that's happening and try and reverse it, try and be more inclusive. We will be better science gets done when you have people coming from all sorts of different perspectives to do the work. It's not just about doing it how we always have done it. So that was an important point they made. Another point they made was we need to remove things like expensive projects that are not generating a lot of science. As much as I love Sophia and I love the notion of hacking a hole, well, a beautifully hacked hole in the side of a 747 and putting a Hubble-sized telescope in the side of it so you can get above a lot of the atmosphere. You can take infrared images that the water vapor will block. It's a great idea, but it's costing us as much as Hubble to run. We can't afford that. If folks want to run this, we need maybe some private consortiums to come in and run it. And that's the way forward, I feel, for that. But having a national asset where we're spending that much money on it, I don't feel is the way to go. And it was recommended that they cut it. Getting back to the point of these long viewpoints, you need to plan great observatories literally decades out. So they made some plans that were all the way out in the 2050s and said, this is the things we need to be looking at, pushing these developments way, way out into the distance. So that's just a broad overview of the ideas and concepts that are put into this. I was away for too long and didn't have time, certainly, to go into too many details on this. And also, things change. They really do. This is the recommendations. And Hubble was a recommendation that came out of a decadal survey. Webb was a recommendation that came out of it. So when we take these seriously, we're able to do great science. And I really very much hope Congress and our nation takes these recommendations seriously and puts the investment into these projects we need to have our next set of great observatories to solve the next great problems. It's how we stay at the forefront of astronomy and astrophysics. And I very much hope that we do. So stay tuned for where we're going to go on that, and we'll see more.